Hello and welcome to section 12.4, which is on angle measures and segment lengths. So theorem 12.13 says that the measure of an angle formed by two lines that intersect inside a circle is half the sum of the measures of the intercepted arcs. So in this example I have drawn here, you have two lines that intersect inside the circle right here. So if I'm trying to find angle 1, that rule says to take the measure of angle 1 would be half of x plus y added together. And I obviously didn't put any numbers in there for x and y, but that is what you would use for that rule. Theorem 12.14, the measure of an angle formed by two lines that intersect outside a circle, right here, they intersect outside, is half the difference of the measures of the intercepted arcs. So now you're going to to find the measure of angle 1, you are going to take x minus y, and you're going to take half of that, half of the difference. So subtract your two intercepted arcs, and then divide it by 2. A secant is a line that intersects a circle at 2 points. So up here, like this one would be a secant, and this one would be a secant because it is intercepting at 2 points. So a chord is a part of a secant. So in this example, I want to find the value of each variable. And I'm going to have to use some of those rules that I just went over, the theorem 12.13 and theorem 12.14, to be able to do this. So, excuse me, to be able to find x, I am going to have to use the rule that stated that it meets outside the circle, which is 12.14. So I have to take the difference of the two. So I have to take 110 minus 30 and then divide that by 2. So 80 divided by 2, that makes my x 40 degrees. And I'm dealing with that circle right there. To find y, I have to use the other rule that states that I add them together, add the two intercepted arcs, and then divide it by 2. So my intercepted arcs, so I'm going to do 1/2 of 30 plus y equals 35. Because 35 is actually this inside. I know that's hard to tell, but the 35 is supposed to be that inside one, so it's the answer to these two added together, the 30 and the y. So 1/2, I have to distribute, half of 30 is 15, and then I'm just going to use 0.5 y equals 35, and I'll minus my 15. So 1/2 of y equals 20, and I will divide that by 0.5. 20 divided by 0.5 is 40. So it just so happened in this case that my x is also, or excuse me, my y is also 40. So they're both 40, even though we use different rules to solve them. Theorem 12.15, for a given point and circle, the product of the lengths of the two segments from the point to the circle is constant along any line through the point and the circle. And there are 3 different ways that you can use this same theorem. Case 1 states that the products of chord segments are equal. So I have, in my example there, A, B, C, and D. So A times B, because those are chord segments, and they have to be equal to the other chord segment, which is C and D. So A times B equals C times D. Case 2 says that the products of secants and their outer segments are equal. So the product of that top secant, I have to add the w and the x together, and then take it times the w. So the whole secant is w plus x, and I have to take that times the outer segment, which is w. And then I have to take z plus y, because that's the whole secant, and then z plus y, and then times y, because that's the outside segment. And the third case The product of a secant and its outer segment equals the square of the tangent. So in this example, z plus y again times the y, because that's the outer segment, has to equal the tangent, which is this x right here. Remember, a tangent just touches a circle on one point, at one point. So then I have an example to go through this where we're going to use these rules. So it just very simply says find the value of the variables. So I need to find y and I need to find z. And I'm going to do y first. So if you go back up here and look at which rule it is here, it's got to be this rule right here, the case 2 rule. So the products of secants and their outer segments are equal. Okay? So I'm going to set this up. So 8 plus 6 times 6, which is the outer piece, has to equal 7 plus y times the outer piece, which is 7. So 14 times 6 has to equal, again, you got to distribute, so 49 plus 7y. So 14 times 6 is 84, and then I'm going to minus the 49, leaving me with 35. And over here I have 7y, divide by 7. So what I have left is y equals 5. This other one, for the z, I'm going to use case 3, because case 3 is the one that says the product of a secant and its outer segment equals the square of the tangent. So 16 plus 8 times 8 has to equal z squared. So 24 times 8 equals z squared. 24 times 8 is 192 equals z squared. And I want to solve for z, so I have to square root 192. Does not come out even. And I'm just going to go ahead and actually find the square root of 192, which is 13.9. Now you could just factor out some perfect squares and just reduce it and leave it in radical form. But in this case, I went ahead and I rounded it, so it's about 13.9 for z, using some of those rules that go with the secant. So bring that knowledge with you about secants and tangents, and we will talk about it more the next time I see you. Have a good night.